Just fiddling with that, I will say that generally when astronomers and physicists hear the word chemistry, their eyes tend to glaze over, or they go to sleep, or if it's in a paper, they just swipe left to the next paper. But I'm going to try to convince you that if you care about exoplanets, you should know at least a little chemistry. And I did have tutorials and I did have math in the talk originally, but it was like way, way long. So I cut all that out. But I left some of those slides in the backup slides. So if you want to see this presentation online, there's backup slides where you can get a tutorial on how to do kinetics, for instance. So it's there. So anyway, I will go on. So why should you care about chemistry? Well, obviously the observations that you're getting are maybe of a composition of an atmosphere. So you need to know how the chemistry has altered that composition, and you need to understand what you're seeing. So you need to know a little bit of chemistry. But also, as Heather talked about this morning, the composition of the atmosphere might tell you something about how the planet formed and evolved. Did it evolve for, oh, does this work? I don't see that little red dot that used to be there. Anyway, this plot on the left, did the planet form very close to its star where you see it for these transiting planets that tend to be close? Did it form behind different ice lines in its disk, you know, a water ice line, or further back on a CO ice line, and then migrate to its present position? Did it form by gravitational instabilities? Did it form by core accretion? If the latter, was it pebbles or planetesimals? And so there are different chemical clues, compositional clues that are left over in the atmosphere. Do you need that might help for that? And you know, that's the ultimate goal. That's a big picture goal that we want of exoplanet observations. Also, the composition might tell us about regions of the atmosphere that we can't probe directly. For instance, deep atmosphere, is there interaction between, you know, core mantle and the atmosphere, and there might be signatures in there. Is the deep atmosphere much hotter? There are chemical clues that might tell us that the deep atmosphere is hotter than we expect. Maybe there's another planet in the system that's tugging it a little, and there's tidal heating going on there. So instead of going into math, I'm just going to talk about 3 different processes, chemical processes that are acting in exoplanet atmospheres in turn. The first is thermochemical equilibrium. It's the thermodynamically favored form of the composition in the atmosphere. So if you have the atmosphere at a certain pressure and temperature, this is a phase diagram, and this pointer is not really working, but got pressure down at the bottom here. On the y-axis is temperature or inverse temperature. Here's a phase diagram for a solid composition atmosphere that just tells you what different forms of carbon, in what molecules of different carbon would like to be in the different thermodynamic regimes. And so methane, it prefers cold, high pressure. CO prefers low pressure, hot. And you get hotter still, you can get C and C+, and so on. Transport-induced quenching happens, you know, you don't have infinite time necessarily to reach equilibrium if you've got winds in the atmosphere or transport in general. That can change the expected result. For instance, the dotted line here, and where's my pointer? So equilibrium is the dotted line. Down deep in the atmosphere, thermochemical equilibrium is maintained kinetically, but as you go up, the winds are transporting gas from a high temperature to a low temperature. You might freeze in the composition when the transport starts to become faster than those chemical reactions. And that gets you out of equilibrium. And finally, there's photochemistry, which is the chemistry that occurs when a molecular atom absorbs a high energy photon or a charged particle from, you know, stellar or galactic cosmic rays or magnetospheric particles, can break apart a molecule, form new things. And again, these things are not stable in thermochemical equilibrium, but they might survive long enough for you to observe them in an atmosphere. So thermochemically, I'll go in a little more detail. It gives you a really good first order prediction of the composition of an atmosphere that works especially well for hot planets. It doesn't work as well for cooler planets. It's very convenient because it just depends on the pressure, temperature, and the relative abundance of the different elements. Here's an example here. If you throw a bunch of elements in a box, and this is from Paul Moliere's an earlier talk that he gave a couple years ago. Again, the elements will want to rearrange themselves in such a way as to minimize the Gibbs free energy of the system. It depends just on temperature, pressure, abundances. There are some analytic solutions available that you can throw in your physics codes for if you're, say, calculating the temperature profile on a planet from a radiative convective equilibrium code. You can add thermochemical equilibrium pretty easy. There's also a lot of public domain codes and databases available now, especially thanks to exoplanet people. And so that's easy. Again, you could do these phase diagrams. Here's another one for carbon, but instead of fixing the composition I did on the other one, this one, temperature is on the y-axis, metallicity is on the x-axis, and astronomers use the term metallicity in a different way than chemists do. So metallicity is really elements that are heavier than hydrogen and helium divided by hydrogen compared to the sun. And so, and it's on a log scale typically. So 0 would be a solar composition atmosphere. 1 is 10 times, 2 is 100 times the solar complement of heavy elements and so on. And so again, you see that for the carbon system, methane prefers low temperatures, CO high temperatures, but as you go up in metallicity, you can even get CO2 dominating. Extra carbon can go to graphite if it's cold, but not if they. So you can play these games. If you have the temperature pressure profile of a planet, you can get the entire composition of an atmosphere just from thermodynamic properties of the different molecules. And you could do this not just for the gas, but also for clouds. So if you hear the term equilibrium clouds, this is what that means. And here's just a temperature pressure profiles for different planets. It's very out of date, so don't look at the labels on these things. But the gray curves are the condensation curves in a solar composition atmosphere. And where those cross the temperature pressure profile, you could have clouds in these atmospheres. And here's a cartoon to better illustrate that. So here, if the planet is cold, up at the top of the atmosphere where you're observing, you might get ammonia, ammonium hydrosulfide, water. If you get a little warmer, you could get mineral sulfides and salts. Warmer still, magnesium silicates and liquid iron could be your topmost cloud that you're looking at. Get warmer still, and the only things refractory enough to be condensing in a hot atmosphere could be the calcium, aluminum, titanium oxides. Of course, transiting planets could be synchronously rotating, entirely locked, as Heather was talking about. So you could have different clouds on the day side versus the night side that are affecting things. And there's, I guess, Pierre Gao will be talking about clouds on Thursday. All right, transport-induced quenching, some examples. This is for Jupiter just because I had pretty slides for it, but it can occur on any planet that has temperature gradients. So if it's hot enough to get to equilibrium, whether deep in the atmosphere or on a day side, but cold somewhere else, then you can have this transport-induced quenching. And so again, the dotted on the thing on the left is equilibrium, the dash on the right is equilibrium. Normally, for instance, on Jupiter, you're cold enough that methane is your dominant constituent all the way through the atmosphere, but there's more CO down at depth than you'd expect up where you can observe it. But this quenching occurs because the transport timescale drops below the chemical kinetic conversion timescale because there are these reactions that have energy barriers. So down in the bottom right, you see a energy diagram for, the reactants have a certain Gibbs free energy. I'm going to give up on that. There's a smaller barrier in this case, for the reactants to go to the final, more stable products. But if you try to get that going in the reverse, the reaction energy barrier is higher. And so it doesn't work as well at colder temperatures. When certain, like methane, water, and CO are sort of exchanging by multiple different reactions, and when that system quenches, all of those molecules quench. So water, CO, and methane will all quench at the same point. N2 and ammonia also have a different quench point, but they'll quench together, whereas other molecules may or may not quench when those main constituents quench. Ooh, I went too fast. Photochemistry, again, is the chemistry that is initiated when a photon, a high energy photon, or charged particle is absorbed. It can break apart the molecule, which is called photolysis or photodissociation. It can get things in a higher energy state, which then makes them more reactive. They react with things. And so you can form a whole slew of new things pretty quickly, both from ion chemistry and neutral chemistry with radicals, if you have an energy source from the star. Okay. Oh, and my son, I always have to include this picture because my son, when he was about 12, drew that cartoon on the right, and I paid him $10 for it, so I want my money's worth. Okay. Oh, I guess I did include an equation, but this is photochemical models will solve what's called the continuity equation, which just describes conservation of mass, and abbreviated form here, again with no pointer, but the partial of the number density of species I with respect to time plus del dot, sort of a flux, and these are all dependent on position in the planet, is going to equal your chemical production minus loss. And there's multiple molecules in the system, so there's a bunch of different I's, and so these are a coupled set of partial differential equations because one molecule can affect what's going on in the other. And it's nonlinear because some of the terms, like the loss term, will depend on the number density I. And there's a bunch of things that you need to put in your photochemical models, and they include things like your reaction list, their rate coefficients. If you want to calculate equilibrium, you need to reverse these things with, so you need the thermodynamic parameters, UV photolysis cross sections, and so on. All right. And the output you get from a photochemical model is something that we fondly call spaghetti plots in the field. And so people either love these or hate these. They can tell you a lot. So I will go into what they can tell you. I don't know if okay. Yeah, I think the battery's dying on that. So volume mixing ratio is a function of pressure. I want to show you, this is for a young directly imaged planet. So it actually is pretty hot at depth because it hasn't gotten rid of the accretional energy yet. And it's cold at higher altitudes. It's far from its star. And so there's very strong temperature gradient here. In the deep atmosphere, and I've lost my mouse. Here we go. Oh, blah. Okay, I'm going to point. Down in equilibrium, dominates down here. It's very hot. Notice that methane is not your dominant carbon, but it's going to increase in equilibrium, and it would eventually take over from CO, which is down here, except for quenching occurs. So you can see the change in the gradient when that quenching occurs. And then it starts getting vertical above that. That tells you, when you see a vertical profile like this in a spaghetti plot, you know that transport is important. And so that stays vertical for a ways until those molecules start interacting with photons. And particularly water, when water is photolized, it produces OH plus H. The H can attack other things. And so you see the gradient in the water and the CO starts to dip to the left. So you're losing your water and CO. That tells you that that is being lost and it's producing other things. For instance, CO2. You see that big, huge CO2 that's peaking right about that region, as well as the different hydrocarbons and oxygen species. When you see a peak like that, you know that those molecules are being, there we go, produced. And so that's just a little shorthand to figure out what's going on. I will go. All right, so I'm going to go through different types of planets in turn and describe some of what we're seeing for the chemistry in these. Starting with giant planets, any hydrogen-rich planet. All right, so very high in the atmosphere, it's what we call in thermosphere in solar system studies, but here's temperature as a function of pressure for an upper atmosphere of a hot Jupiter HD 209458b. And Tommy Koskinen has played a kind of fun game where he's moved this planet to different distances from a star, 1 AU, 0.5 AU, 0.2 AU, and then wherever it is now, closer than that. And originally you have, hydrogen is a homonuclear molecule. It doesn't get rid of its energy very effectively. And so the thermosphere is hot, but when you move it too close, there's a critical point at which it gets really hot. So we're talking close to 10,000 Kelvin, at which point it's a very expanded upper atmosphere and you've got cooling as this hydrogen is actually blowing out of the system. So it's called hydrogen. Ooh, I should keep my microphone there. Sorry. So it's being carried away. They call it a wind, of the hydrogen, and it's dragging some heavy stuff with it. And that tends to cool the atmosphere, but you end up with a very extended thermosphere. Here is a distance scale on the side, and you can see it's in terms of the planetary radius. So if you're observing atoms or ions, which is basically all that's left over in a very hot atmosphere, here's neutrally single and singly ionized and neutral oxygen and carbon in a model being carried away along with this hydrodynamic escape. If you're looking at the transit in lines that are sensitive to those atoms or molecules, like in the UV and sometimes in the visible, then the planet is going to look huge. Okay. And the heating is actually from the absorption of X-ray and extreme ultraviolet radiation from the host star. So the closer you are, the greater that flux is. All right, a little deeper down, I'll start with equilibrium. This again are these sort of phase diagrams. We got temperature on this axis, this function of metallicity, different molecules. Methane, again, likes it when it's cold. CO likes it when it's hot. But as you increase the metallicity, you continually increase the CO. Whereas methane, you start to lose the hydrogen, you start to lose the methane. CO2, notice here, it starts to get really abundant. In fact, it can dominate your atmosphere as you increase the metallicity or lose the hydrogen equivalently. So the reason I'm showing this is because you can play games. Normally when you've got a spectrum from the star, your bread and butter way to analyze the spectrum is to do retrievals. But I also think it's very good, in fact, this is becoming popular now, to do grids of forward models, predictions, because there might be a lot of information in the real chemistry that helps you explain what's going on. And it comes in handy. Like I've had people say, send me emails, say, I've got this planet that is 10%, X molecule. And I'm like, no, you don't. So it really provides kind of a sanity check for what's going on, preferably with not just equilibrium, but disequilibrium chemistry too. Here's again, still in the infrared photosphere of a giant planet. Quenching is not just in the vertical direction, it's in the horizontal. So this is, again, mole fraction, a classic paper by Marcelino and Gundes, mole fraction to function of pressure, a bunch of important molecules. Each line here is a different longitude on the planet. So again, hot transiting planets are hot, tidally locked or synchronous rotation, whatever you want to call it. Hot on the day side, cold on the night side. Methane prefers it cold. So on the night side, you got a ton of methane, but you're losing the CO. On the day side, you don't have much methane, but you have CO dominant. And so if you're looking at the planet across its full orbit, the chemistry is going to change in equilibrium depending on which side of the planet is facing you when you're observing it. But in the real atmosphere, there's winds. For instance, there's winds, strong zonal winds that can carry the gas from the day side to the night side faster than it can equilibrate. And that tends to homogenize the atmosphere. Where's my cursor? And so you see in this plot, this has photochemistry and it has kinetics, which can capture photochemistry and quenching. And you can see that the atmosphere in the region that you're most sensitive is much more homogeneous. And this is done now frequently in 3D models, and it's a little more complicated than that 2D model that you show here. But the net result is that you are homogenizing your atmosphere. So again, top curve would be methane being more abundant on the day side. Less abundant on the day side than the night side. Day side is too hot, and the equator is hot. So there's less, but if you have kinetics in the model that contributes to quenching, then it homogenized. Okay, and now we have some direct evidence for photochemistry in exoplanet atmospheres. We might have had some hints of it before, but finally we have a little spectrum with a little bump. So this is the hot Saturn WASP 39b. And you see that dip here. Absorption is up on these plots. So there's a little dip from absorption of SO2. You can see that it's very sensitive to metallicity. So there's the things that say Vulcan 5 times, 10 times, 20 times. This is from the recent paper by Shami Tsai. And SO2 is extremely sensitive to metallicity because there's 3 heavy elements involved. And the more heavy elements we have, the more SO2 you're going to have. CO2 is similar, but SO2 is even a more sensitive indicator of metallicity. So it's great that we can see that. So what's happening in this atmosphere? This is a hotter atmosphere where CO is your dominant carbon. Water, where's my cursor? Anyway, N2, H2S is your dominant form of sulfur in equilibrium in a hydrogen dominant atmosphere. So in thermochemical equilibrium, it would just be a straight line going all the way up. But because there's photolysis, H2S is actually very weak bond, so it's easily destroyed both by photolysis and by atomic H. When the atomic H attacks the H2S, you can form all these other species, including S2, SO, S, and SO2. Notice that SO2 is only peaked in that one region. Fortunately, we can see that one region, so we're getting the spectrum of SO2. It has also bands at longer wavelengths. Oh, that paper isn't published. Never mind. Okay, so Heather talked about this bimodal distribution of the intermediate sized planets is what I call them. So super Earth, sub-Neptunes, they might have once been similar, but the rocky core with a hydrogen dominated atmosphere, but you move the planet too close to its star, or if it's small and can't gravitationally bind that hydrogen, you'll lose it. There's population synthesis models. Here's one by Mordicini that just shows that he starts with a bunch of planets of different distances from a solar-like star and lets things evolve. And some of these planets drop to bare cores. There's a gap with nothing in between because the hydrogen puffs the planet out. And so the planet looks bigger when you've got the hydrogen there. Okay. And so probably these sub-Neptunes, at least the ones that we know have some hydrogen left in the atmosphere, could have extremely variable atmospheric compositions. Just a quick little thought experiment. So for a typical photospheric pressure where you're sensitive in your observations, fix the CO to O ratio. And if you say a 500 Kelvin region, you start with an atmosphere that looks like Saturn maybe for 10 times solar. But as you increase the metallicity, you can get to a state where you're no longer hydrogen dominated, but you're actually water dominated. Lose the hydrogen further, you could get CO2. And for hotter, same thing, only now CO instead of methane, and that takes up some of the oxygen, so less water. Or you can mess with the CO2, C to O ratio, because depending on where that got its heavy elements, it might be enriched or depleted in carbon or oxygen, and so on. So you can play these little games to help define the possible parameter space that you should be exploring. This, I will move on kind of faster, but it's just the spaghetti plots that say the same thing. You end up with CO2 being very affected by metallicity. All right, but all of those models ignore the fact that there's an interior. So there could be a core or mantle that's liquid. And if the atmosphere is interacting with the liquid, then you have to worry about that equilibrium that can occur. So that's a big topic now on what happens to your, your accreted gas like hydrogen in any water or anything else, and how it interacts with the core. How will that affect? And that's a really great future topic, because I think nobody's really talked about the chemistry that will occur in the atmosphere when this all happens. And the reason we're doing all this is because there's this degeneracy in the mass radius diagram that Heather showed earlier. So are these Sub-Neptunes rocky worlds, bare rocks with a thick hydrogen atmosphere? Are they mini Neptunes where you've got a smaller rock iron core, but you have a lot of volatiles like water and maybe a thinner H2 atmosphere? These are all mixed together in some cases too. Or do you have a water world where you've got maybe the top layer might be hydrogen, maybe overlying a liquid ocean? This is Madhu's favorite planet. And so there's degeneracy, and atmospheric observations can help resolve that degeneracy and also tell you what's going on deeper down. All right. Excuse me. One way, there are fun games you can play if you have a Sub-Neptune, but it does have a surface, so the atmosphere is not very deep. This is Jingting Yu, which I think is in the audience as well. So she's taken a temperate Neptune where you've got methane, water, ammonia. A lot of it, it's not ammonia dominant, but ammonia is important. Mixing ratios, function temperature. So a deep atmosphere, the photochemical products that you are producing, remember there's peaks, those are the photochemical produced things, flow down into the deep atmosphere, where when they get to the higher temperature regions, they can reform those parent molecules. But if you put a surface there, suddenly the surface may not be at a high enough temperature and pressure to get you back that things. So you do progressively lose things like ammonia that are more photochemically fragile in favor of N2. And similarly, you lose some of the methane in favor of CO and CO2. So just the presence of a surface, and this is a chemically inert surface in this model, can change your composition. And if you have an ocean, this is a liquid water ocean. So people play these fun flow chart diagrams saying, starting with your observations and your observed features, you go through this thing and it can tell you what type of planet it has. Is it a massive atmosphere with a high metallicity, a massive atmosphere with low metallicity? Does it have a surface, ocean surface, and so on? And I like Rainu, so I've put this one here. But if you have an ocean that is completely equilibrated, you could have CO2 is your dominant species, N2 is your dominant carbon species, nitrogen species. Oxygen is both in water, which is going to be saturated at the surface. You could have water clouds if the temperatures are cold enough. And so all of this photochemistry is produced from those things that are in equilibrium with the liquid water ocean. I need to speed up. So now we're talking about terrestrial planets, rocky planets, but the ones close to the star, you could have a lava world. Got it. Where you're hot enough that maybe on the day side, you've got magma. Okay, so a magma ocean atmosphere is going to be interesting. So these are various classic papers on that. So you can, I give up on these things. You can have things like SiO, O2, and atomic metals atmospheres for these things that you might be able to detect. Depending on your oxidation state of your lava, your magma, you might get different results and what temperature it is. All right, so terrestrial planets that are more in the temperate zone, and this is not my specialty, but there are a lot of different exploration avenues that are being pursued. Of course, biomarkers are big ones right now, and formation of prebiotic chemicals is a big thing, but also there's some, here's one that's talking about, is O2 itself going to be a biosignature? Does it depend on the volcanic outgassing flux from the planet? Does it depend on where the pressure and how does these things change? And I think the bottom line of a lot of these studies is, oh, we have to pay attention to where we're putting our top boundary because we're not resolving photolysis well enough. Ooh, sorry. And I didn't talk about any lab stuff. There's a ton of laboratory experiments that are going on now that are giving us great work, not just on hazes that I'm showing here, but also on gas phase compositions. So I don't want to sell that short. And there's a lot of studies on photochemically produced hazes. And I think maybe Peter will talk about some of those Thursday. So bottom line, chemistry does matter. You can use equilibrium as a good starting point. I think I like the trends of people using full disequilibrium chemistry model grids as another resource to throw at exoplanet spectra to try to understand what's going on. And I will quit there. But I'll say don't presume anything for these compositions. Explore a very wide range of parameter space when you're doing these studies. Thank you.
Thank you, Julie. We have time for questions. Covered a lot of ground. Sure, there's some great ones out there. Yeah, let's start in the room and you first. Is it on?
So I like working on giant planets because I don't have to worry about the boundary conditions as much. So you do need to know temperature and pressure, and you do need to know sort of the strength of atmospheric mixing, you know, how strong is the transport, because that can affect where quenching occurs. But in the models that go deep, I don't need to care about the boundary because everything will get to equilibrium at depth. If you're talking about interior, okay, so I don't know the answer of how the interior might affect things. You do have some of those products that are interacting at that depth that might condense, and so you wouldn't see some of the effects of that. So the metals, silicates, if you're hot enough, I think it might matter. And it depends on whether you can equilibrate, what's the equilibration time, if this stuff is liquid, and so on.
Yes, we have a question online here, asking how the CH4 and the CO quench at the same pressure level, but have different chemical timescales.
They actually will have the same chemical timescale if that system is the only thing operating on those things. So down deep, well, in all the things that I've seen, they do quench at the same point. Maybe Shemi will disagree. So actually, I'm trying to remember his paper. Sorry.
Hi, Ananya Bhattacharya from University of Michigan. So thank you so much for this wonderful talk. You mentioned metallic clouds, I guess, of zinc, sodium. I was wondering, like, if they are at such high altitudes, there's also convective activity going on. What would be the role of possibly heterogeneous chemistry with these metallic clouds?
Yeah, it's possible. We don't know. There are certain things, especially on iron is a good catalyst. There's other things that are good catalysts. So there hasn't been a whole lot of work on heterogeneous chemistry in these particular types of clouds that I know of. Somebody can correct me, but that's a good avenue for future exploration.
Yes, we have a question. Does the size of planet influence the composition models developed using CH or CO ratios? If yes, how?
In terms of the, oh wait, did she? No, she used a microphone. Yeah. So does the size of the planet affect things like the C to O ratio? I'm trying to think. I mean, the C to O, the bulk C to O is controlled by where you formed and what happened to the atmosphere afterwards. I don't think so, unless you've got interactions with the interior that could affect your things, like carbon in contact with a liquid iron is going to go away. So there are processes that can affect the C to O ratio in the atmosphere. The big question is, can you hide any of these elements? For instance, you can't see N2 directly. You can see ammonia. And so you really aren't going to get a good handle of the nitrogen content of the atmosphere unless it's cold enough to have ammonia. For carbon and oxygen, we do expect to see most of the carbon and oxygen species in most of these planets, but it turns out that some of them are a little harder to see than others. And so we're just learning whether we can, in fact, detect things like CO and so on.
Thanks for a great talk. You said for small planets that the top boundary layer is very important in determining the chemistry. How is this the case for, because you also make the decision for giant planets, right? So
Yeah,
how important is the boundary layer for giant planets then?
Yeah, the top of the atmosphere is important for everything. So some of these models just didn't go high enough to capture all the photolysis was occurring in one layer at the top. And this giant planet, people learned this a long time ago and have moved their things up. So as long as you're, I usually go like ridiculously high because that's what I do. But as long as you're above the region where as long as you're not optically thick right in your top layer at any wavelength, you're okay.
Thank you for the talk. For transport-induced quenching, is temperature the main driver of the transport, or are there other processes that can force the gases upward from the interior, like storms or something?
So yeah, down deep, if you've got a convecting atmosphere, then convection is dominant. If you've got a radiative, it tends to be atmospheric waves, like on planets that I know about in our own solar system. There's atmospheric waves that are generated by storms or anything else down deep that propagate upwards. They can break and mix. And so your effective mixing ratio tends to increase with altitude, or inversely with pressure. And so it tends to be wave dominated in irradiated regimes like your stratospheres, and then convectively dominated down deep.
Yes. So this question asks, for photochemical models with complex organic molecules, including aromatics, do we have UV cross sections available in the community?
We do for some and not for everything. So there are a lot of laboratory needs. There's molecules I'd love to add to my models, but we don't have either cross sections or thermodynamic parameters to fully reverse them. And that second thing can be a bigger problem. But there are ways to calculate both now. I think computational chemistry has come a long way. And so you can get things like rate coefficients and even and thermodynamic parameters and even cross sections theoretically now as well. And that can be faster sometimes than spending 3 years to get one number in a lab.
Sure. This question might be hard to answer. So what is the mathematics behind quenching? How does one exactly estimate elemental composition using quenching?
Okay, so you have to calculate the kinetic timescale, and I actually have the kinetics tutorial sort of in there, but you have to know what the dominant reactions are that affect the quenching. And I guess Shamisai has some good papers on that. There are some, and then you have to know the transport timescales, and so there are some ways to estimate that tend to be sort of order of magnitude type calculations. And that is, again, a tutorial I have in the backup slides on this talk, but they are approximate. It depends on chemistry. It depends on transport. There are some prescriptions. There's, procedures you can follow to do transport. I mean, to do this quenching. Where does it quench? As a practical tip, if you're doing, say, a retrieval and you're doing a equilibrium-based retrieval, you can actually just have the quench point as a free parameter in your retrieval. And so that might be a good way to go if you have one of those thermochemical equilibrium-based retrieval methods. But otherwise, you can either do the kinetics calculations yourself. It's a lot easier to actually do this within a photochemical model than it is to follow these procedures. Sometimes there are some public domain photochemical models out there that you could use.